Oh, it's behind the sun. Okay, I just could have sworn you did. Maybe. Okay, this is started, so whenever it's like, I don't know, you're ready because it's 5:57. Let's go.
Good evening. Can everybody hear me? No? Okay, we're working on it. Hang on. Is that any better? Yeah? A little bit more? Okay. Is that good? How's the sound in the back? Good? Okay, excellent. Hello. I am Angela Metler. I'm an administrative assistant in the president's office at South Dakota Mines. Welcome to this month's STEAM Cafe. STEAM Cafe is a partnership with Hay Camp Brewing and South Dakota Public Broadcasting. So we appreciate their support and we appreciate your support as well. Every time we do this, we broadcast live on Zoom. So we have a Zoom audience tonight also. So I'd like to thank you guys for attending and for those who are watching on Zoom. At the end of the presentation, we will have a Q&A with our presenter. If you are watching online and you have a question, go ahead and type it into either the chat box or the Q&A box, and I will make sure that it gets answered live. If you're in here, just raise your hand and we'll get your question answered. Yeah, so that's about it. Without further ado, tonight's presenter is Dr. Donald Teets. He is a professor emeritus in the South Dakota Mines Department of Mathematics.
Yeah, okay. I recently retired from the School of Mines after teaching mathematics there for 35 years. I regularly taught calculus courses there. There will be no calculus tonight. If you look in math books, what you often see is little margin notes, little historical vignettes about the players in the mathematics that's being discussed. Sometime around 1998 or 1999, I was teaching something known as the method of least squares, which is a data analysis tool. And I saw in the margin note of my calculus book, it said, blah, 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 blah. The mathematician Carl Friedrich Gauss invented least squares. And I just happened to pick up, just in the next day or two, I just happened to pick up a different calculus book. And it said, blah, 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 blah. The mathematician Legendre invented the method of least squares. And I got very curious about that because here are these two completely different accounts of it. Both of them were mathematicians, but they were working in astronomical problems. One was looking at the orbit of the asteroid Ceres, and the other was looking at the orbit of a comet in the discussion of this method of least squares. I got really curious about it, so I went and found the original paper of Gauss, written in the early 19th century. It was in German. My colleague at the time, Dr. Karen Whitehead, it turns out, PhD in mathematics, but her bachelor's degree was in German. And Karen translated that article, and the two of us, after it was translated, then there was another period of trying to understand it. And eventually we wrote an article about it, published it in the Math Journal, and it won an award. And that just launched me on a 2.5 decades of investigation of problems that lie in the intersection of history, mathematics, and astronomy. And one of the great problems in that intersection, history, mathematics, and astronomy, is the problem that we're talking about tonight, the discovery of Neptune. And we'll do the two of the three, history, astronomy, and mathematics. We'll leave one out. And if you're lucky, we'll leave out the right one. So, again, I've been working in this area for now 2.5 decades, and this is one of the premier problems. The discovery of Neptune was brought about by mathematicians. So away we go. Let's just start with the known solar system from antiquity to the late 18th century. If you go out and look at the night sky, observe the night sky enough times, pretty soon you recognize that some of the bright little things are moving with respect to the others. Those are the planets. The planets have been known, well known, the 5 so-called naked eye planets have been well known from antiquity until, from antiquity, essentially all of the astronomers, everybody who looked at the night sky knew these 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn, and of course the Sun and the Earth. So for the greatest length of time, people thought that was it. There are no more planets. It's just those 5. Until William Herschel. In the 18th century, William Herschel was fundamentally a musician. He made his living giving music lessons. He was a musician, but his passion was astronomy. And he was not only an amateur astronomer, but a telescope maker. He was making the best telescopes in the world at that time, but he had absolutely no idea that he was making the best telescopes in the world at that time. So just by chance, just by observing the night sky night after night, he found something that was moving against the background of fixed stars. And oh, I love this picture, Herschel's 40-foot telescope. Wouldn't you love to have that in your front yard? Our neighbors would complain, I'm quite sure of it. So this is Herschel's 40-foot telescope, but it's not the one that he used to discover the planet Uranus. Here's a Chandra X-ray observatory photograph. So this is not what Herschel saw when he saw the planet Uranus, but I love the photograph, so I put it in there. So Herschel discovered Uranus in 1781. It was an accidental discovery. He just was observing the night sky night after night after night, and he found something that was moving. So this was really extraordinary because everybody at that time thought that the 5 naked eye planets, that was it. That was the end of the story. But here's another one. So there's a curious fact about the planets of the solar system. There was maybe a promise that there wouldn't be any math tonight. Is that right? Well, we have to amend that ever so slightly, just a wee little bit. Bode's law is a rule that describes the planetary distances from the sun. It has no real scientific basis. It just seems to work. It's a curiosity. To this day, it is a curiosity. It was first published by Johann Bode in 1772, and really it's just a little pattern recognition. Here's Bode's law. In the left column, you see the list of the planets. In the middle column is their actual distance in tenths of an astronomical unit. An astronomical unit is the distance, the average distance from the sun to the earth. It's about 93 million miles. So astronomers measure things within the solar system in astronomical units. It's a very convenient unit of measure. So the actual distances, these are in tenths of an astronomical unit. So Mercury is 0.4 astronomical units from the sun. Venus, 0.7, 7/10 of an astronomical unit from the sun. The Earth, of course, is by definition 1 astronomical unit, so 10/10 of an astronomical unit. Mars, about 1.5, and so on. Well, Bode's law is in the right-hand column, and maybe you can see how it works. This column of numbers right here, we're just doubling at every step. 1, 2, 4, 8, 16, 32. Then take that number, multiply it by 3, and add 4. There's no scientific basis for this whatsoever. It just seems to work. And so now you see the Bode's law distances in the rightmost column there, and you compare those to the actual distances, and there's a striking similarity between those two sets of numbers. 4 and 4, 7 and 7, 10 and 10. Oh, Mars is just a little bit off. 15 Bode units, 1.5 astronomical units is the true distance, and 16 is what Bode's law predicts. And the same for Jupiter. Jupiter's right on, and then Saturn at 100, well, that's pretty close to 95. So here's this new discovery, Uranus. Its true distance, 19.2 astronomical units, or 192 Bode units. And there's Bode's law, and it seems to still work pretty darn well. Oh, you may have noticed that there is this question mark, this empty space in here. So astronomers began to believe in Bode's law so much that they thought there must be something out there at 28 Bode units, 2.8 astronomical units. The asteroid belt is exactly what's there. A German, Xavier van Zach, was the publisher of an astronomical journal, and he put out a call for people to look for that missing planet at 2.8 astronomical units. The Sicilian mathematician, Sicilian astronomer, Giuseppe Piazzi, discovered the first of the asteroids in 1801. After he observed it for 41 days, it became a daytime object. It got so close to the sun in terms from our perspective that it became a daytime object, and so it's lost. And based on those 41 observations, the mathematician Gauss was able to calculate its orbit and predict where to look for it when it became a nighttime object again. And that's the problem that got me started in the whole thing, Gauss's discovery of Ceres. That was the start. That launched me into the whole study of astronomy and mathematics. After Ceres was discovered and rediscovered, other asteroids soon followed. There's Pallas, Juno, Vesta. Ceres and Pallas are right at 2.8 astronomical units, which just fits perfectly with Bode's law. So now, that fills in the missing step, the missing line in Bode's law, and it makes the astronomers of the time even more convinced that Bode's law was real in some way. And to this day, there is really no scientific basis for Bode's law at all. It's just a curiosity, but it's a pretty darn good curiosity. So, as the observations of Uranus began to accumulate, astronomers sought a full understanding of the new planet's orbit. So now, what does it take to understand the planetary orbits? There are certain fundamental tools that astronomers use to understand the orbit, and we'll go just ever so slightly into that toolkit. Kepler's laws, those are the fundamental tools. Kepler's laws of planetary motion, you may have heard about them in a high school science class, you may not have ever heard of them. The first law of planetary motion simply says that the orbit of each planet about the sun is an ellipse. Roughly a century after Kepler, Newton showed the dynamics of why that orbit should be an ellipse. We don't care why, it's an ellipse. The second law is a bit of a computational law. The line from the sun to a planet sweeps out equal areas in equal times. So you can see the planet that's drawn in on that elliptical orbit right now is fairly close to the sun. It has to move faster when it's close to the sun to sweep out that area in a given length of time, and then slower when it's far from the sun to sweep out that same area in a given length of time. So it's traveling slower, you might say, when it's far from the sun, and faster when it's close to the sun in a manner that keeps the areas the same. And let's see, there's at least one mathematician in the audience, so there's Kepler's second law in mathematical terms. Oh well. The third law is a mathematical relationship between the time that it takes a planet to orbit the sun and the planet's distance from the sun. There's Kepler's third law at the bottom of the screen. T for the period, the time that it takes to get around the sun, and D for the distance. For the Earth, the computation is ever so simple. It takes 1 year, that's our time unit, and the distance from the sun is 1 astronomical unit, so the left side of the equation is 1 and the right side of the equation is 1, and we're all happy. For the other planets, it's a little more complicated, but the same law holds for all the planets. All right, so here's what Kepler's third law tells us about the planets of the solar system. Their relationship between the period of the orbit and the distance from the sun is very predictable. They just fall right along this perfect curve that describes that Kepler's third law. All right, so if you have enough observational data, Kepler's laws can be used to predict exactly where to look for a given planet on a given day. When I was still teaching at the School of Mines, this was a regular sort of thing that I had my students do. We would be able to calculate exactly where in the sky you could look for Jupiter on a particular day, and we'd get it right. I mean, it's a very, very well-established, well-known, well-functioning computation. So, Uranus, the new planet that Herschel has just discovered. As the years go by, more and more data is recovered regarding where it is at a given time, regarding its orbital path. And in fact, from 1781 forward, the planet had been discovered. They knew of they gathered data in the context of knowing that that was the planet Uranus. But they were also able to look back at old data. Tobias Meyer had unknowingly recorded the position of Uranus in 1756, and John Flamsteed as far back as 1690. So now they had more than 100 years of data about the location, the position of the planet Uranus. And with that data, they were able to calculate the orbit quite well. Unfortunately, Uranus was not quite in compliance with Kepler's laws. It was violating the laws. And so obviously people began to speculate, why is that? Why is Uranus not behaving in the way that it should according to Kepler's laws? The problem, some people thought that the data that didn't fit was just poor observation by these ancient astronomers, the older astronomers, Flamsteed and Tobias Meyer. They just didn't have very good equipment. They weren't very good at it. They probably made mistakes, so let's just ignore their data. But other people had a different idea. Other people included John Couch Adams. He's one of the stars of our show tonight. John Couch Adams was one of many astronomers who had a different idea about why Uranus was not behaving as it should. Yeah, there. Adams was a mathematics student at Cambridge University in 1841, and he read about the discrepancies between Uranus' orbit and the prediction where it should be. He started to work on the problem after his graduation in 1843, and he and many others at the time theorized that the orbit was being distorted by the gravitational influence of another larger but as yet undiscovered planet. So orbit computations work something like this. Essentially, all orbit computations start off as what's referred to as a two-body problem. So if you want to understand the orbit of Mercury, you look at it as a two-body problem, the sun and Mercury. If you want to understand the orbit of Venus, you start off by looking at it as a two-body problem, the sun and Venus, sun and Earth, sun and Mars, and so on. Separate two-body problems. But in the case of a planet like Saturn that has a very, very large neighbor, Jupiter, the orbit has to be done in two steps. You do first of all, calculate the orbit as a two-body problem. So you first solve the Sun-Saturn two-body problem. And then you correct Saturn's orbit by knowing how Jupiter affects it, how it perturbs it. So it's a two-step process, the prediction and the correction. So Adams' idea was to reverse the process. They understood the orbit of Uranus, or they thought they did, but yet it was being perturbed. And so it was being perturbed by an unknown object. So Adams' idea was, okay, where is this unknown object and how big must it be in order to perturb the orbit of Uranus in the fashion that it does? So Adams believed, and again many others believed, that indeed there was another planet out there, a massive planet that was perturbing the orbit of Uranus. So the idea was to use the perturbation, how much does it deviate from its original orbit, the originally calculated orbit, and by knowing how much it deviates, you may be able to predict the location and the size of the planet that is perturbing it. So this is a matter of timing. I hope you can see, this is a little bit smaller print from the back there. I can point to a couple of things here. This is the inner orbit is the Uranus orbit, the outer orbit is the Neptune orbit. And this is just a collection of position data for the years leading up to the discovery. Here's Neptune in 1720. Here's Uranus in 1720. They are so far apart that there is no perturbation. That is, the gravitational influence of Neptune is non-existent on Uranus. They are just too far apart. And as the years go by, you see here's Neptune in 1750. Here's Uranus in 1750, still much too far apart for there to be any significant gravitational influence between these two. But as the years go by, let's see, by 1790, here's Uranus, and here's Neptune. They're starting to get a little closer together by 1790, and now the gravitational influence of Neptune starts to be felt on the planet Uranus. Adams' timing couldn't have been better, because here's Uranus in 1800, here's Neptune in 1800. They're getting close enough together that they actually affect each other. In particular, Neptune perturbs the Uranus orbit. By 1810, here they are, and now the tug is forward. That is, Neptune is tugging Uranus forward in its orbit. So it's going a little faster than it should. 1820, they pass each other. And by 1830 now, Neptune, the slower planet, is starting to tug the other direction. It's starting to slow Uranus down. And of course, this shows up in the observational data. And so, had Adams lived 100 years earlier, he never would have been able to solve this problem because the planets were not aligned correctly, quite literally. All right, so 1820 was sort of the magic time there where Uranus passed Neptune in its orbit. So how far out should the unknown planet be? Well, Bode's law was exactly the tool that people believed in to answer that question. And so the Bode's law answer, next power of 2, 128 times 3 plus 4, 388, or 38.8 astronomical units out. So that was Adams' hypothesis. This unknown planet, which we now refer to as Neptune, must be 38.8 astronomical units out there, and knowing that allowed him to calculate its effect on Uranus. So here's Adams' prediction following an extraordinary amount of computation. Adams predicted in October of 1845 where to look for the unknown planet. And the right side there, I'm sure, is too small for you to read, but that's just as well. This is a typical page out of Adams' calculations. This particular page here probably cost me at least 40 hours work. My trying to understand it, my first attempt to understand it was out of a a celestial mechanics textbook that was in French. I don't read French, so I read the mathematics and leave out the words. And it turns out that some of the words that I was leaving out really mattered. And so I spent a huge amount of time just trying to understand these basic formulas right here. But eventually, I nailed them. I got them all. Here's Adams' computations that he published after the fact. He did this all with pencil and paper, of course, and tables of logarithms and trigonometric tables. In fact, I even read that he had a day job of some sort, but he would come home after his day job and he would sit and do pencil and paper calculations. He had a younger brother who looked over his shoulder. The younger brother didn't really understand what was going on in the computations, but he knew how to do arithmetic. And so if Adams added 3 and 5 and got 9, the younger brother would squawk and Adams would correct it. And so I duplicated, I think that I estimated that Adams did about 5,000, just multiply, divide, add, subtract, another 1,000 trigonometric function evaluations, trigonometric and logarithm function evaluations, and he didn't make any mistakes. In his published version, it is just spotlessly accurate. So I did it all in Excel. Excel, I say, has pencil and paper and a lot of patience. I did it in Excel with no patience. And I came out with, just in the middle of the calculations, you can just extract a line from Adams and a line from my work, and boy, they match. They just match. So I'm pretty sure I understand the method pretty well at this point. So Adams attempted to deliver his results in person to the Astronomer Royal of Great Britain, George Airy. Boy, doesn't he just look like a 19th century scientist? George Airy wasn't in when Adams stopped by the Greenwich Observatory, and so Adams left his calculations, left his prediction with an assistant. Airy was interested when he looked at the calculations, but the observatories of the time, just like observatories today, have a fairly rigorous schedule that they follow. They schedule months in advance for people to use the telescope and do a particular investigation. And Airy was a busy guy. He had a strict observing schedule, and so, well, Airy did not carefully investigate or pursue Adams' prediction. He basically just kind of brushed it aside. Adams was totally unknown. He was like 24, 25 years old, fresh out of college. He had no reputation at all, so Airy just basically ignored him. Meanwhile, across the English Channel, Urbain Le Verrier. Here's a stamp, a modern French stamp honoring Urbain Le Verrier. Urbain Le Verrier was a professor of astronomy at the École Polytechnique. He started working on this same problem in 1845, and he came to the conclusion that the only way to explain this was that there was a large, massive planet beyond Uranus that was perturbing the orbit of Uranus in this way that was being observed. So Le Verrier had a somewhat different plan than Adams. He divided the zodiac, that is, the zodiac is, you might say, the path of the planets through the night sky, through the stars of the night sky. He divided it into 40 zones of 9 degrees each, so that would cover the entire circle. And one zone at a time, he would put a hypothetical planet out beyond Uranus and hypothesized that that planet was in that particular zone on January 1st, 1800. Then he would calculate, okay, if there was a planet out there at that time, what would its mass have to be to cause these observed perturbations in the Uranus orbit? How far out did he put the hypothetical planet? Well, there you have it. Bode's law, 38 astronomical units. Why not? Le Verrier concluded that for all but one zone, the mass that must be necessary to cause the perturbation, if the outlying planet was in any zone but one, then the mass was impossible. And within that remaining zone, he would try 5 different positions. So he would take that 9 degrees and divide it into fifths. So what is that, 1.8 degrees each? And he would put the planet at one of those positions and calculate what its mass would have to be in order to cause the perturbation that was observed in the Uranus orbit. And he found that one choice perfectly accounts for the observed errors of Uranus. Le Verrier was a very well-known professor at the time, and his status ensured that his work was widely read. Airy read it in June of 1846 and saw that Le Verrier's prediction matched Adams' prediction very closely, and so suddenly Airy got excited about it all. Le Verrier's work was known all over Europe. It was published, it was read by all the astronomers of Europe. Everybody knew about Le Verrier's work, but nobody but Airy and a few close friends knew about Adams' work. So Airy finally springs into action. The Greenwich Observatory is essentially booked solid. They don't have any observing time. And so he calls his friend James Chalice in Cambridge, at the Cambridge University, and asks him to start the search with the Cambridge telescope to search for this new planet according to Le Verrier and Adams' predictions. So Airy's proposed search area was 30 degrees by 10 degrees. If you have a telescope, if you've looked through a telescope, you realize that that is an enormous area of the sky to look at. My telescope, when I look at the moon fills the field of view. The moon is about 1/2 degree. And so my telescope has roughly a 1/4 degree field of view. How many 1/4 degrees can you fit into that 300 square degrees there? A whole lot of them. There are just so many places to look within that 30 by 10 degree field that it's just about impossible to cover that in any reasonable length of time. So the search area is in the constellation of Aquarius, and that red box there outlines the extent of the search area that Airy proposed. The search begins July 29th, 1846. Here's the so-called Northumberland telescope at Cambridge. The Duke of Northumberland, wherever that is, provided the money for this telescope. So to this day, that telescope exists and is known as the Northumberland telescope. So Chalice carefully recorded the position of every object in his search. He would search a particular part of the sky, and recorded at that time means pencil and paper diagrams of all the stars that you see in that particular field of view. So you point the telescope, you make a sketch of all the stars that are there, and then you move on, you do it again and again and again. To check the accuracy of his instruments, Chalice compared 39 star positions recorded on the 30th of July with the same ones recorded on August 12th. What you're looking for as an astronomer, if you're looking for a planet, you're looking for something that moves from day to day. The stars do not. Their relationship to one another, their pattern is unchanged from one day to the next. If there is a planet there, it will move from day to day, and that's the way you find planets. So he's comparing 39 star positions on July 30th with the same ones on August 12th, and he determined that everything was fine, nothing to get excited about. Oh, had he compared 10 more stars on his list, he would have found that one had moved between July 30th and August 12th. So Chalice was looking at Neptune and he didn't know it. I have a diagram that an image that I've created from, you can get planetary software, or I should say planetarium software for your personal computer. So this is just images that I clipped out of my computer set to July 30th, 1846, and August 12th, 1846. And you can see in this picture that one has dramatically moved. Well, it's too easy. That's Saturn. Nobody could mistake Saturn for anything else. If you've ever seen Saturn through a telescope, gosh, I look at Saturn through my telescope, and children come up to the telescope and look through that, and it's just wow, it's just like in the books, in the astronomy books. There is no chance that anybody could mistake Saturn for an unknown planet. The image is probably small enough, maybe the people in the very front can see this, but there is something else that has moved from July 30th to August 12th. Right there it is, just a little tiny speck. And it's easy to see if you draw a line between these two stars and draw a line between those two, you can see that that little speck has crossed the line. That's Neptune. And that's what Challis overlooked when he was comparing the July 30th and the August 12th images, we'll say. These were probably hand-drawn sketches of what he was seeing. Challis had it right in front of him within his grasp, and he just didn't get it. So Adams and Le Verrier are still working to revise and improve their predictions. Le Verrier's work is very much in the public eye. It's been disseminated all over Europe. All the astronomy, all the observatories in Europe are aware of it, but Adams' work is unknown to essentially everybody except for Airy and Challis. So here are revised predictions from Adams on September 2nd of 1846 and Le Verrier August 31st of 1846. So these are what, 3 days apart, 2 days apart. And you can see this is Adams' prediction of where to look for Neptune. Here is Le Verrier's prediction. They're really quite close together. They're close enough together that if you're given either one of those predictions, you'll find it. You should find it, let's say. So it's well within the search box that Airy had proposed. It's right smack in the middle of it, in fact. So the Paris Observatory started their search. Challis in England at Cambridge. The Paris Observatory starts their search, but they abandon it quickly because it's interfering with their regularly scheduled observations. So Le Verrier writes to an astronomer, actually an assistant at the Berlin Observatory, and asks him to search according to the predictions. And wow, September 23rd, 1846, Gala in Berlin receives the request from Le Verrier, and he finds Neptune the first night he looks for it because the prediction is so darn good. Word spreads all over Europe in a few days, but it's all Le Verrier because nobody's even heard of Adams. He's a nobody. Here's again the Adams prediction, Le Verrier's prediction, and right there is where Neptune was actually discovered. So Le Verrier's prediction is a little bit better than Adams', but Adams' prediction is easily good enough to have discovered Neptune. So the French get credit for this. Le Verrier is the hero. But the British won't be outdone. They announced that, well, okay, actually Adams had already predicted this independently. He'd made accurate predictions for finding Neptune a year earlier. And they pointed out that, well, you know, this Challis guy, he actually did observe it on the 12th of August. And this just made the French people furious. They were just angry about this. I think the British and the French, they get angry over a lot of things. And this was just one of many things that they just could not stand. So here's a suggestion that the French cartoonists made about how Adams made his discovery. There's Adams with his telescope looking across the English Channel at Le Verrier's logbook. And so they're saying that he stole this from Le Verrier, that Le Verrier deserves the credit and Adams just stole it from him. Adams is vindicated, though. He was very good about it. He did not protest. He did not complain. He was just very complimentary to Le Verrier and was asked for no credit of his own. His work was published. That's the work that I looked at, that I read carefully. And it became very clear to everybody that his method was completely different than Le Verrier. There was no way that he could have copied Le Verrier because they were totally different methods. And in some ways, his work was superior to Le Verrier's. It worked more from first principles and a little bit less from the, let's divide the zodiac up into those 40 sections and then kind of one at a time eliminate them. So it was also clear that if Airy had acted on Adams' work from the very beginning, he almost certainly would have found Neptune first. Again, Challis had his telescope pointed at Neptune and just didn't know it. So all's well that ends well. Adams and Le Verrier ended up having the greatest respect for each other. They became friends of a sort. They lived in different countries, of course, spoke different languages, but they were on good terms as the years progressed. They remained lifelong friends. And that is all I have to tell you tonight. The next is we'll have the mathematical details of Adams' method, and you might want to have 2 or 3 beers before that one. Not today. So that is all I have to tell you, and I'm happy to take questions if you have questions. Yes, sir, Hank.
How much does Mars and Jupiter impact
Impact
the orbit of the Earth?
the orbit of Uranus. Earth, okay. The short answer is all of the planets influence all of the other planets. If you're a person like me, Mars' influence on Earth is absolutely undetectable. If you're JPL, NASA, you know how much Mars influences Earth because it matters to them. If you're trying to, if you're doing calculations that are so, that need the accuracy to be so great, as JPL and NASA do, then you have to take into account all of those perturbations. But the perturbations are quite small because the planets are quite small. Jupiter and Saturn have significant influence on each other and have significant influence on Uranus. So those have to be considered. Roughly speaking, all the planets influence all the other planets. Some of them much more than others because they're much more massive, and of course the distance matters too. Does that answer your question? Okay. Colin.
Bode's law is a very interesting relationship, but what's the cause of that?
It's as far as I know, it is pure coincidence. Oh, I didn't mention that Bode's law failed. It fell on its nose when Neptune was fully understood. I don't think that appeared in here. Bode's law predicted 38 astronomical units, and the correct value is about 30. So it's significantly off for Neptune. I think that there is some work that shows there might be an underlying physical law that really explains the Bode relationship, but it is not well known, and essentially it is just a curiosity. It just kind of works. It's looking for a pattern. The pattern is there. The physical cause, don't know.
Your next research paper.
If I could nail that down, that would be worth something. Yeah.
Well, because of the elliptical orbit, isn't that astronomical unit, does that vary?
So the astronomical unit is defined as the average distance. In the elliptical orbit, the sun is at one focus of the ellipse, which means it is not at the center of the ellipse. So the Earth, for example, is sometimes closer to the sun and sometimes further from the sun. If you take the total distance and divide it by 2, that gives you the astronomical unit. So it is essentially the average distance from the Earth to the sun.
All of them are very independent all the time.
All the planets?
All the astronomical units of all the different planets.
Well, the astronomical unit is specifically defined in terms of the Earth's orbit. And so when we say that Jupiter is 5.2 astronomical units from the sun, it means that its average distance is 5.2 times as far as Earth's average distance. So the astronomical unit, you don't have an astronomical unit for each planet. You have one astronomical unit that is defined in terms of the Earth's orbit, and then all of the other orbits are sized according to that unit. It's about 93 million miles, and again, it's the average distance of the Earth from the Earth to the sun. Yeah?
I read recently a piece that I didn't understand about the fact that your atom was subtracted leap seconds from yours.
Oh, leap seconds. Yeah, okay. So we need George Gladfelter here because he could give you a concise 2-hour lecture on your question. Let's see. So why is there a leap year? The day is defined in terms of one Earth revolution, the Earth spinning on its axis. And the year has to do with the Earth traveling around the sun. And so the early calendars, the Julian calendars, have exactly 365 and a quarter days per year. But eventually we find that that's not quite right. It's just a little bit off. And so 325 and a quarter days gets adjusted every 4 years. We stick in a February 29th into the calendar every 4 years. Oh, does anybody know the exception to that? Yeah? Oh, Travis.
Every 100 years we take it back out, but every 1,000 years.
No, not every 1,000. 400.
Oh, 400 we stick it back in.
Yeah, that's right.
That's why we had it in 2000, but then we got.
So 2000 was a leap year. The year 2100, for those of you younger people here, 2100 will not be a leap year. Even though it's divisible by 4, it's not a leap year. Okay, so your question about the leap second has to do with now we get into measuring time not by astronomical events, but rather by cesium atom behavior, cesium atom clocks, atomic clocks. So those atomic clocks measure time in a different way than the astronomical way. And they have to be adjusted so that those two correspond to one another perfectly. And exactly how that adjustment takes place, the leap second, I really do not know the details of that. Right, so there's astronomical measure of time. And oh, it's even more complicated than what I've told you. There are solar days and sidereal days. There are tropical years and sidereal years. And I mean, there's a lot to that. But the leap second, I think, has to do with how atomic clocks and astronomical timekeeping correspond to one another. And I think that's about all I can tell you about it. Again, ask George Gladfelter. He'll give you a 2-hour lecture on it, and you still won't know the answer. Becky.
I have a question. Do the number and sizes of the moons around the planet, such as Neptune and its various moons, could that affect the polarity of these?
Oh, absolutely. It does affect it. But the moons, the question is, do the various planetary moons, like moons of Jupiter, moons of Neptune, moons of the Earth, do they affect the planetary orbit? And the answer is yes. Every speck in the universe that has mass affects every other speck in the universe that has mass. But the influence is very, very, very small. It's negligibly small. The Earth's moon, we tend to think of it as fairly big, you know. Let's see, what is it? Well, say it again? 1,400 miles across? Okay, so that's the size of the moon. Do you know what the ratio of the mass of the moon to the mass of the Earth is? What fraction of the Earth's mass is one lunar mass? 1 to 60? It's 1%. So 1 to 60 is probably pretty close, but it's 1%. And so if you have this moon, our moon orbiting the Earth, it looks pretty big out there. It's not. It's just really very, very small mass compared to the mass of the Earth, and so its gravitational influence is very, very small. Another measure of the relative size of things, so you think about the center of mass of the Sun-Earth system. Where do you think the center of mass is? It's somewhere between the sun, center of the sun, center of the Earth. Anybody know that? The distance from the center of the sun to the center of mass of the Earth-Moon system is like from here to Sioux Falls. It's 400 miles. And so again, the relative masses of these objects is so grossly out of scale that the influence of one on the other is just negligible. And the moons, the planetary moons, are the same. They are just so much smaller than the masses of the planets that they have very little influence on the planetary orbits. But they do have some. Yeah. Yes?
So speaking of mass, I'm curious about Le Verrier's method of calculating the position based on the mass of Neptune have to be.
I'm not quite hearing you, Bryce.
So I'm curious about Le Verrier's method of calculating the position based on what the mass of Neptune would have to be. What is the state of knowledge of planetary mass at this point in history, and what is that knowledge based on?
Well,
bearing in mind that I'm an English professor.
Oh, I can answer that fairly concisely. Herschel. So he discovered Uranus in 1781. I read a paper of Herschel that was written right around that time, late 1780s, in which he calculates the mass and the density of the planet Uranus. His value for the density and NASA's value for the density of Uranus, they're the same. It's astonishing. And where does that come from? Well, so to calculate density, you need to know the mass and you need to know the volume. And the volume you can get by looking at the thing. If you know how far away it is and you know what its diameter is, angular diameter, does it subtend an angle of like 30 arc seconds or 12 arc minutes or whatever. Basic trigonometry will tell you the volume of that object. As far as the mass of the object, Kepler's laws. Kepler's third law will tell you something about the period of one of Uranus's moons and relate it to the distance of that moon from the planet. So now Kepler's third law is just the tool that you need to calculate the mass of the planet. And if you know the mass of the planet and you know the volume of the planet, you got the density of the planet. And again, Herschel came up with a density of Uranus that I think is 0.23 times the density of Earth. And if you look it up in NASA's files, they say 0.23. It's just amazing. He did that in 1780, I don't know what, 1788, 1786. Does that answer your question somewhat? Yeah, it's Kepler's laws. Kepler wrote Kepler's first and second laws, 1609. Kepler's third law, 1619. They are 400 years old, and they are still the bread and butter of what NASA uses to fling Apollo astronauts around the back of the moon. It's astounding. It's 400-year-old math that is still at the heart of the study of anything in orbit. Yes?
I've read in the past that the three-body calculation is kind of intractable, but you're looking, or Adams was calculating Uranus and Neptune and the sun.
Yep.
Is that correct? So is that three-body calculation not that difficult?
It's not a three-body problem. It is a two-body problem, Sun and Uranus, to calculate the orbit of Uranus, and then a perturbation problem to see how Neptune influences Uranus. So it's two separate calculations. It is not done as a three-body problem.
So two-body problems.
Yeah, that's one way to look at it. It's looking at a two-body problem and then trying to understand how that two-body problem is, how the reality deviates from the answer to that two-body problem. So it's a predictor-corrector method. The three-body problem, oh, you got 10 seconds to hear about that? Or maybe, might take a whole minute. You might have heard of the James Webb Space Telescope. Yeah? James Webb is in orbit around absolutely nothing. That absolutely nothing point is a solution to the three-body problem, a solution to what's known as a restricted three-body problem. So the three bodies in that case are Sun, Earth, James Webb Space Telescope. If you could park the James Webb Space Telescope exactly at one particular spot, it would stay there. It would never move. It would stick there forever. That's an example of the three-body problem. But you're absolutely correct that the three-body problem, the general three-body problem, is not solvable in closed-form mathematics. You can approximate it all you want, and with big, powerful computers, the approximations are very, very good. But you cannot solve the three-body problem, meaning you can't take three gravitationally interacting bodies and know exactly where they will be, the three of them, at any particular time. But again, you can come as close as you want by good computing and just high precision computing.
Just run it through your handies.
Absolutely, just run it through. Well, maybe just run it through your Excel spreadsheet, because the computations that you can do on an Excel spreadsheet with a personal computer are far more powerful than anything that NASA had available to it when they landed people on the moon. So yeah, you don't need a supercomputer. Nah. Anything else? Yes? Oh, now you're talking about an expanding universe, and you are completely out of my knowledge base. I am interested in things in orbit, which means essentially solar system. And anything outside the solar system is, you got to talk to somebody, you got to talk to a real astronomer. I just don't have any answers for that.
So I don't remember which one of the two outer planets revolves sideways.
Oh yeah. I think it's Neptune.
And so there's some belief that it's a rogue planet that our solar system captured. Is that a reason why it might be outside of Bode's law?
I would just give a short opinion that is no. Bode's law is just fiction. Bode's law is fiction that just works a lot of the time. And so Neptune, rogue planet, yeah, maybe, I don't know. Bode's law, nah. That's what I think. Becky, did you have another question?
Well, it kind of piggybacked off that. I understand there's the speculation of verification of another planet that they are investigating, and I was wondering if Bode's law would support
Well, I think you would have to answer that retrospectively. After that new planet is discovered, then you see, does it fit into Bode's law? Yeah, and you all know about, do you know Father Guido Sarducci? You know who he is? And do you know about the planet that he talks about? Turns out there's another planet that is orbiting the sun exactly opposite the Earth, so we can never see it. And everything on this other planet is exactly the same as it is on Earth, except for one thing. They eat corn on the cob this way. So, there's a non-answer to your question.
I read it in New Scientist, I don't know.
Yeah, well, really, Bode's law, you would have to apply it retroactively, and say, oh, here's this new planet, it's this far out, and now what does Bode's law say about it? But Bode's law really fails badly at Neptune. Back when Pluto was a planet, I think it fails pretty completely with Pluto's distance and orbital periods. So Bode's law it's just not really true. It's not really science, but it's a darn good coincidence in many, many instances. I think that's all I could say about it. Yeah. Well, I guess you can call anything a law if you want to. I mean, Bode's rule, would that help you? It's Bode's not really a law. Yeah, I don't know the history of that. Shall we quit then? Have another beer? All right, thank you.
I'm not going to get too close because I don't want to set the squealing off, but we do this every third Tuesday. So September 16th is the next date, and that'll be a presentation from Lori Vega from Ellsworth Air Force Base talking about some of the South Dakota Mines student projects that have worked on problems at Ellsworth Air Force Base. So September 16th, hope to see you here, 6 o'clock.